Cutting inserts. In this section, we will learn how to select a cutting tool according to the workpiece material and type of cutting process. There are many parameters to consider when choosing an insert. It is important to carefully select insert geometry, grade, shape, size, nose radius and entering angle, to achieve good chip control and machining performance. The rake angle, geometry, and feed play an important role in the chip formation process. The rest of the heat is usually evenly distributed between the workpiece and the tool, as can be seen in the animation. The maximum heat generated during cutting is on the top part of the insert, in the chip breaker, and close to the cutting edge. This is where the maximum pressure from the material is, and the friction between the chip and carbide causes these high temperatures. For this reason, removing the chip from the cutting area by breaking it during the chip removal process will reduce the transfer of the generated heat removed from the environment with the chip to the cutting tool. The insert rake angle is the angle between the top face of the insert and the horizontal axis of the workpiece. The rake angle can be either negative or positive. Based on that, there are negative and positive inserts, where the clearance angles are either 0 or several degrees plus. A negative rake angle tool is generally stronger, but it generates more force and requires more power than a negative or neutral rake angle is preferred for rough turning operations, particularly for cast iron. Lead angle. The entering angle is the angle between the cutting edge and the feed direction. This angle has an effect on chip formation, the direction of cutting forces, and the length of the cutting edge during machining. Insert nose radius. The nose radius is an important factor in turning operations. It affects the quality of the machined surface, the chip formation, and the insert strength. Small nose radius, ideal for small depth of cut. At a small nose radius, vibration is reduced, but insert strength is also reduced. A large nose radius is preferred for higher edge strength, high feed rates, and large depths of cut. Lead angle. The entering angle is the angle between the chip control in turning. Long chips are one of the main problems for turning operations. The reliability of the continuous turning process is a significant necessity of mass production and automatic manufacturing systems. Long chips are the main problems for continuous turning operations, and chip break is difficult during the machining of ductile steel and superalloys. Chip formation during machining negatively affects worker and tool safety, workpiece quality, tool life, and energy consumption, while also reducing operational efficiency. To alleviate such problems, continuous chip formation during machining must be controlled through chip breaking. Insert shape, number of cutting edges. The insert shape should be chosen in accordance with the geometric profile on the workpiece. The largest possible corner angle should be selected to ensure insert strength and reliability. The triangle insert has 3 cutting edges on each side. If the insert is negative, a total of 6 edges can be used. The cutting edge angle of the C-type insert is 80 degrees and has high cutting edge strength. The round type insert provides the strongest cutting edge. It also provides the best surface quality due to the large radius. However, the long cutting edge produces relatively wide chips and it is difficult to break the resulting chip. In addition, the load on the insert increases due to the large contact area and long cutting edge length. C and W type inserts are commonly used for roughing due to their larger point angles. D and V-type inserts are generally used for finishing surface treatments since the nose angles are smaller. While having less strength creates a disadvantage, their ability to reach more part details offers an advantageous processing opportunity. Inserts are used as the cutting edges for cutting tools for turning and milling. The insert geometry, tolerance, dimensions, and terminology are all based on ISO standards. ISO uses a coding system of numbers and letters to identify the shape, size, and key parameters of inserts. Square inserts have 4 cutting edges. If the insert is negative, there will be a total of 8 cutting edges. Rhombic inserts are the most preferred insert type in external turning operations. Inserts are used as the cutting edges for cutting tools for turning and milling. The insert geometry, tolerance, dimensions, and terminology are all based on ISO standards. Type D and V inserts are generally used for finishing. The insert has less cutting edge strength. The use of 55 degrees or 35 degrees depends on the geometry of the workpiece being machined. The trigon insert has 3 cutting edges per side. If the insert is negative, then a total of 6 corners can be used. The cutting edge angle is 80 degrees and offers high cutting edge strength. The round insert offers the strongest cutting edge. Additionally, due to the large radius, it provides the best surface finish. However, there are a few disadvantages. The long cutting edge produces relatively wide chips and is difficult to break it. Also, due to the large contact area and the long cutting edge length, the load on the insert increases. A turning insert coded according to ANSI and ISO norms is given on the screen and can be seen as coding for a C-shaped insert. 12, 04, and 08 codings are indicating that the cutting edge is 12 mm, the insert thickness is 4.76 mm, and the insert radius is 0.8 mm. The PM is the manufacturer's option. Here, P represents the steel material and M represents the mid-level cutting conditions for machining. Insert geometries and productivity. The productivity potential for a manufacturing process is all about the interaction between material, cutting tool, and machine. Choosing the right insert and parameters suitable for the material can allow higher cutting values while extending tool life. By using higher cutting data, it is possible to increase productivity and at the same time significantly extend tool life. You can see how machining time changes when cutting insert geometry and depth of cut in machining a steel workpiece. Tool wear. Wear is the loss of material that occurs on the insert's contact surfaces. Although we take all the necessary precautions to use the inserts within the maximum limits, wear occurs on the cutting edges. During the machining of materials, all inserts wear and continue until they complete their life. In other words, tool wear is inevitable. During chip removal, different parts of the cutting tools are exposed to different types of wear, and as a result, the life of the cutting tool is reduced, it becomes dull and its insert break. Flank wear occurs on the free surface of the cutting edge. This is the most seen type of wear and is caused by friction between the workpiece material and the hard particle in the insert. Crater wear is formed on the chipped surface of the insert. It is caused by the chemical reaction between the workpiece and the insert and increases with cutting speed. Excessive crater wear weakens the cutting edge and can cause breakage. Built-up edge consists of welded materials onto the insert by pressure. This type of wear is very frequent when machining sticky materials such as low-carbon steels, stainless steels, and aluminum. A low cutting speed increases the built-up edge. Notch wear is when chips are welded on the cutting tool by pressure, followed by excessive localized damage to the cutting edge. It is a frequent type of wear when machining stainless steel and heat-resistant superalloy materials. Plastic deformation occurs when the cutting tool material softens due to excessive heat. It can be seen when the cutting temperature is too high during machining. Thermal cracks during the chip removal process can be seen on the cutting edge. Cracks may appear on the cutting edge due to the sudden change in temperature from hot to cold with the use of coolant. Thermal cracks are mostly seen in milling operations with interrupted cuts. Edge chipping or fracture type wear occurs as a result of the overloading of mechanical tensile stresses on the cutting edge.